Hey guys, what's going on? So today we're talking ISO spin. This is going to be the last video before we get into talking about quarks. Quarks are interesting. We're going to see a lot about how they are. We're going to see a lot how we draw from this video to make sense of quarks. So anyways, if you like this kind of content, make sure to hit that like and subscribe button. And I'll see you guys. Actually, not I'll see you guys, but let's get into the content now. Remember to go into my Patreon page if you want exclusive content. All right, so let's get into the material now. Okay, so we're talking isospin. What is isospin? Well, let's recall that local symmetry comes about via interaction terms, okay? We had our U1 invariance, and that gave us something like electric charge, okay? We had our electromagnetic field vectors that were doing the interactions for us to maintain that local invariance. For our SU2 invariance, this is going to give us something called isospin, and we're going to see specifically how this comes to play. Okay? The first thing we want to do, this is going to be a relatively short video. There's going to be no exclusive content on this. The first thing we want to do is we want to recall that Noether's theorem for internal symmetry looked like this. Okay? And Q, which was our conserved quantity, looked like this. Okay? So, okay, we can define this guy, right? This guy's not too hard. This guy is just the change in our field when we do a Taylor expansion. Right? So that comes from this guy right here. Okay? So that's that change in our field. Recall also that the globally invariant free Lagrangian looks like this. Okay? So, therefore, if we say that this here is our conserved quantity, then this here is the conserved quantity. Not too difficult to see how this plays out because this guy came from here, okay? Or is this guy right here. This derivative, Lagrangian with respect to the derivative and the zeroth term, well, that's going to be, it's the derivative with respect to this, so that's why we have this right here. All right. So, what is, So this is our conserved quantity, right? So Qi, so I here is different than this I. This is a complex number. This I refers to this I. And that's something interesting to note, right? And we'll see how that plays out in a few minutes here. This guy here can be thought of as right there, okay? So we have this now, we have this. We talked earlier about leptons and how packaged into leptons we have electrons and their counter neutrino, if you will. They're not really counter, they're coupled with each other. Not using the wrong language here. For every electron there's going to be a neutrino. Okay? And we talked about that in the last video. So let's take a look at it. We could take a look at this for I3, right? Because the whole point here is that, okay, for every sigma, there's three of them, we have a conserved quantity. So for every Pauli matrix, there's a conserved quantity, which is important to note. Okay. So let's take a look at this for the third Pauli matrix, because the third Pauli matrix is the one that's diagonalized. That's this guy right here. If you recall the other Pauli matrices, I'll write them out, we have 1, 1, 0, 0. This is for I equals 1. And then we have, for I equals 2, we have, it was I, negative I, 0, 0, like that. Okay. And we'll take a look at, for 1, 1 right here. Oh, there's that negative. Yep. For that negative. But anyways, let's take a look at this. So here's what it is, right? So, and what we end up with is these should actually, we had an I out here. This is why this I multiplies with this sigma to give us real numbers in the entries. And then we have, so when we do this multiplication out, we get this. Okay, so this means that we can assign 2 eigenvalues to this transformation, right? The idea again is that we have an SU2 transformation of the Lagrangian. Okay, well, if it's a transformation, there's got to be eigenvalues to that transformation. The eigenvalues are right here, okay? And what's important to note is that the diagonalized matrix, right, in this case, sigma 3, is going to be the thing that gives us those eigenvalues because it's diagonalized. If you've taken linear algebra, then you can recall that you need a diagonal matrix in order to get the eigenvalues. Okay, the conserved quantity that can only be in 2 states, leading us to this conservation of spin. The other 2 Pauli matrices can give us eigenvalues. We just need to diagonalize them, and in order to do that, we need to use a different basis. Okay, but again, the point here is that there's only two values, 2 eigenvalues that can be used here. So here's our Q1 and here's our sigma 1, right? We're just doing another example. So when we do this, we actually get a mixing of the terms, and since the 2 mix, we can't have distinct eigenvalues for them. Meaning that the conserved quantity can only be measured by Q3, okay, unless we go into a different basis. So the point here is that, again, this is somewhat of a short video. This is what isospin is. These 2 guys here are the isospin values that we're looking at, right? So, okay, it's spin. We're calling it isospin. Its spin has 2 discrete values in this case, and it's isospin because we're not doing this specifically for just an electron or a spin of just a neutrino. These values will actually tell us something about if we're measuring neutrinos or electrons, not their individual spins. Okay? And what's going to be super, super interesting here is that when we go into quarks, we need to consider a little bit of group theory in order to figure out exactly what the conserved quantities are going to be in that case. And what we're going to find is that in the case of SU3 in quarks, the conserved quantities are going to be color charge, right? So we're going to get 3 conserved quantities, each of which is going to have their set of eigenvalues. Those conserved quantities are going to be red, blue, and green color charges. Okay. We also need to identify the particles in the case of SU3. We're going to do that in the next video also. And yeah, this is a relatively short video, primarily because I really just want to get our feet a little bit wet with the idea of isospin, how we measure eigenvalues of the transformation of a Lagrangian. And yeah, there's no exclusive content on this video, so this one's completely on me. Anyways, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to hit up my Patreon page if you do want some exclusive content that you won't find here on YouTube. And with that being said, I will see you guys in the next video.